Welcome to Lesson 3, Example 3, and what it is asking us to do is calculate the maximum shear stress in the joist of Example 2. And since I erased Example 2 already, we're going to go ahead and do it again because the more practice you're going to get at doing free body diagrams, the better, and shear and moment diagrams. So let us continue. Point A, we'll call this point B. That means this is going to be, you'd call it reaction at A, and this could be reaction B. Well, I'm just going to call it BY and AY. Does not matter. You can call it whatever you want. We're going to start with the sum of the forces, or sum of the moments about, let's do it about B this time. I believe we did the sum of the moments about A. Let's do the sum of moments about B. Mix it up a little bit. And you go from left to right. We said that's positive, so you're going to have a positive AY times 14 foot. And then you have to figure out what your equivalent distributed load is, which I need to get my calculator out, but it's going to be 500 pounds times 14 foot, which is going to be 7,000 pounds, I believe. Yeah, that makes sense. 14 times 500 is 7,000 pounds. Are we looking at the right thing? I believe so, yes. Yes, we are. 500 pounds times... see, that's not right. I jacked it up again. I did the same thing last video. Alright, it's 80 PLF times 14 foot. 14 foot times 80 pounds per linear foot equals 1,120 pounds. That's why it's always good to check yourself and kind of take a look at what you're doing. Alright, now that's going to, where's what, summing it about B, so that's going to be going this way, so that's going to be negative. So we want to add a negative, or you can represent that any way you want, but I'm going to say add a negative 1,120 pounds times halfway is 7 foot. And then I'm going to add, we have a negative 500 pounds. Since that's going to induce a negative moment. And then we have 4 foot. And we want to solve for AY. And AY equals, we're going to have 1,120 times 7 plus 500 times 4. Since that's all negative, that's going to go to the opposite side. You divide it by, it's going to become positive. You divide it by 14, you're going to get 702. And I believe that's what we got last time. 702.9, let's say, pounds. I believe that's correct. 702.8, 702.9. Yeah, we're good. Alright, then we're going to do the sum of the forces in the y direction equals 0. And we're going to solve for BY. AY is a positive 702.9 pounds. Minus 1,120 pounds. Minus 500 pounds. Plus your BY. And solve for BY. And it's going to be positive. That should be intuitive for you by now, because this is all going to be, unless you have an overhang situation, you're always going to have positive moments on a simple beam for your reactions. I say moments, positive force in the y direction. It's going to go up, unless you have a uplift condition. So 1,120 plus 500 minus 702.9, BY equals 917.1 pounds. Alright, now let's go ahead and put it in here. Let's say 702.9 pounds, and again 917.1 pounds. And now we can go ahead and move on to our free body diagram. Remember, we're getting rid of this on your shear and moment diagrams. You want to not have your equivalent load. You want to go back to your distributed load. Alright, that looks good. Let's move on. Okay, you have V as a function of X. And that's close enough to lining up. We'll call it good. Let's go a little bit faster. U up 702.9. Let's define the units over here. We're going to go down 80. So 80 times how many feet? 10 foot. Equals 800. So 702.9 minus 800 is negative 97.1. So we're right below it. Negative 97.1. Then we're going to, that's going to be a linear slope because this is uniform. If it's not uniform, if it's a trapezoid or if it's a triangle non-uniform load, this will actually be, you can see it would be the same as when you go to a moment diagram. The slope would start at a maximum and it would be slowly going down. So you'd be kind of like this type of, that's probably not the best, but it'd be more like that type of curve. Alright, anyways, moving on. Then we go down 500. Negative 97.1 minus 500 equals negative, close enough, 597.1. It's kind of hard to read. I apologize, but we're going to move on because that is not our negative moment, our max moment. And then we're going to subtract 80 times 4 foot to finish it off right here. So we're at right there. And we get negative 917.1. And that's where we thought we needed to be, because obviously when we go back up, 917.1, we go to 0. Alright, so that we can now figure out our Vmax, which is our maximum shear. And we look down here, let's say, okay, on the positive side, we had 702.9, and on the negative side, we had 917.1. So 917, kind of think of it the absolute value. 917.1 is going to be your max. And that's going to be in pounds. Alright, so we've got our Vmax, and we can move on. We don't need to go do our moment diagram. We already did that on example 3. So let's look at our simplified equation, because we can use our simplified shear stress equation because this is a rectangular section. Excuse me. If you remember, the simplified equation is shear stress equals 3V over 2BD. And V, once again, is 917.1 over 2. And then B is going to be your width. And I believe it was the 2x12 wood joist. So let's actually, we can just BD, we can look at the area, because B times D is your area. And we had a 2x12. Area is 16.88 or 86. Hold on, let me take a quick closer look. 16.88, and that's on the section properties of standard dressed sawn lumber, and that's on page 45. It's that table. So 16.88 is B times D. This is area. B times D also equals area, because it's 2x12, and it has what? B times D. And of course, we're not talking about, there's nominal and then there's actual. Nominal is the name. You're saying it's a 2x12. Actually, it's not 2x12. It's probably what, 1 3/4 times, no, this is not right, 11.5 maybe even less than that. That's nominally, you say in name only, it's a 2x12. But actual dimensions are going to be less than that. Alright, so we said it was 16.88 inches squared. Let's go ahead and do the calculation on that. 3 times 917.1 divided by 2 divided by 16.88. Your answer is 81.5. Let's follow the, actually it's easy, you have pounds over inch squared equals PSI. And here's your answer. psi, 81.5 psi, and I checked that out and it matches up. Alright, so we'll take this information, which is your stress and shear. Your shear stress equals, and then from the last 81.5 psi, and then your stress from bending, we take it from last one, and it looks like they put it down here, is 1170 psi. Then using this information, obviously if we had axial loads, you could look at that as well. What's your force in axial? But we don't have any axial loads, so that's going to be, actually, well, let's write it up there, equals 0. So as you can see, you have different loads in each. And this bending and the axial are actually going to combine to in each other. For instance, if you're going to have what we call a beam column, where you have a column like so, and it's fixed down here. That shows that it's fixed, typically, is how you draw that. Except it's not a squiggly line, it's here. It's more like this. So you have a beam, and it's, you know, let's say in reality this is like sunk into the ground 1,000 foot, so it's not going anywhere. And you have this, I'll call this a P load, which is axial. And then you also have, let's say, another something coming in and hitting it right here. And we'll call this, let's call it V. So what this V is going to do is going to induce a moment down here. You're going to have that load times this distance right here. So let's say that's 10 foot. And that's going to, moment is going to equal V times 10 foot. So if you think about it, okay, it's on this side, it's going to deflect this way, right? And you're gonna, so it's going to be compression on this side and tension over here, and you also have compression. Let's say it's just a pole. That's a steel pole, and you have this remember, axial compression or axial stress equals P over A, and let's say it's 10 psi. So, well, let's say 100 psi. And then you're also getting the bending stress. So you're going to have, that's in compression. Then you're also going to have compression over here. So you're actually going to have to add your maximum bending stress to your axial. But you have axial 0, so you don't worry about it. And shear and these two are separate. So typically you'll add these, and you don't need to add the shear. Hopefully that wasn't too confusing, and I'll do some more videos on there in time, but we need to finish this up right now, so here we go. So what they were asking is you have the shear stress and you have your stress and bending, and you need to figure out, okay, well, what type of wood am I going to use? And we want to take the shear stress and the bending stress and go look at the table, and we take a look on page 44, and we look at this, go down, we look for species and grade that has greater than these two, and it looks like Douglas fir, which has allowable of force of bending. This is allowable because it's capitalized. That's what we do. Is 1,450 psi and an FV of 95 psi for a 2x4 to 4 inch second and 2 and wider. And these are both greater than those, and you can kind of show that like this is greater than FB equals 1170. And since they're both greater, this would be what you want to use.